day in a year. What I have on my point today? There are periodic signals, but they also are non-periodic signals. Let's take a first example from the circuits theory. It's a classical genre, let's say. I have DC source, I have capacitor, I have one resistor, and this will be U as a function of t. It will be our voltage pulse. I will switch at the time equals to 0. Okay. So, this battery is a source. It's nice Philip Harris Limited, England, Birmingham. 5 microfarads capacitor. And 600 ohms resistance. I can. Here it is. I push the switch. All such kind process yield a pulse like this time. It will be E power of t. In our case, E is approximately 27 volts, and of 1 against RC. You can calculate. Just to show the pens, 1 second, I will save it to. No, I don't need. I want to save waveform as a reference. Yeah, I have saved. My waveform as a reference. Whoa. Here it is. White waveform for 600 ohms and 5 microfarads. I have this capacitor with 1 and 1/4 of the microfarad. How do you think? How will change the voltage if I use this capacitor? 1 and a quarter of microfarad.
Это ультрафиолет faster.
Amplitude will change.
No.
No. Only rate of here it is. You can see 4 times faster. The same effect. .4 kiloohms. What will be checked? What we'll see if I switch from 600 ohms to 2.5 thousand ohms.
It'll decrease slower.
Slower, or let's take a look. Ground to the ground. Wait 1 second. Yeah, someone. This is ground, it's okay. Maybe I need to change the scale. Yeah, I used a different scale. Resistance bigger, and we see process going slower. If I use smaller capacitor but larger resistance, what we will see? Yeah, scale. Why?
Hey, sorry.
Hello, hello.
Yes, I'm feeling late.
See, I put them in the same time scale. So.
Also, wir haben nicht Schluss? Oder wir haben noch?
No, you can see they are virtually the same. It's a small difference. Never mind. So, what I'm trying to say, I'm just playing a bit, but in our practice, in power engineering, it's a very popular signal. But what kind of signal? It is determined. Yes, we have mass expression for any moment of time. But is it periodic? All the mechanics, what I showed with this machine, was about periodic signal. What if voltage or current or anything repeats, no problem, we can decompose it to, or present as a Fourier law as a set of ideal DC and one ideal DC component and set of ideal AC components, and use what we knew from the basics of electrotechnics. It's applicable, no problem. But this one is continuous, is determined, but never repeats. What shall we do about such kind of signal? It is very possible when we switch something on or switch something off. what shall we do? We need some tools because what we know from basics of electrotechnique is not usable. This one is not. It is DC current. No. It's AC. No. It's a pulse. It's a pulse of decaying exponent. How? I don't want to switch it all the time. I'll use small setup. I'll use a generator producing 1 microsecond pulse each 2 milliseconds. Capacitor and I will have resistance here, and this will be my signal. I want the test setup to show everything on the screen. We need a tool for such kind of signal. Tool set, let's say. I'll use this variable condenser. It's made for air ministry. Well, it's not older. It's not only older than me, it's older than my father. Possible. Yeah, it's approximately 1918, so my grandfather, maybe. Yes. But it's in perfect condition. No. Resistance.
1980. Not Soviet Union, Soviet Union. Soviet Russia.
Yeah, this one is good. And this one. I will also use this resistance box. So. Capacitor is 1 nanofarad and resistance will be 100,000 ohms. It will be good for my scope. Generator. 1966. It's quite hard to get modern with such parameters. Because such monstrous outputs are not needed. And the best about it is this side. This device is a property of mine. Let's assemble my network. Would be nice to get self-assembling schematics. But couple moments I will get everything working. Or not everything, or not working. Okay, what I need. I need a ground wire. Okay, come on. I need a ground wire because I need a ground wire. This one is okay. Let's say the red one will the signal and another ground wire and scope connection. Disconnected. This one is connected. I can use so earth goes here. And this switch is here, and I don't need this one is no longer needed. Why? I see some oscillation because I made a mistake. This is wrong. Who's here? Yes. Here it is. Our exponential signal. Now it's a sequence of pulses. Not one pulse, but a sequence. And what can we do with such sequence? At this moment, we have a sequence of pulse. One pulse. I have created artificially a sequence of pulse. If you want, I can change time scale. Here it is. Sequence of pulse. Activated by generator. Sequence of pulse. Repeats?
Yes.
Repeats. So I can treat the sequence as a periodic signal. And I can try to perform a Fourier transform on it. It will be, let's say, legal. So, I have one pulse. Here is one pulse. I have made with the driving generator, with the help of my generator, sequence of such pulse. All together they form a kind of periodic signal. You can see, repeats, 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 have a frequency. If you want, I can switch to period. Here it is, it has a period of 2.3 milliseconds. 2 milliseconds, I have promised 2 milliseconds. Now, we come with a period of 2 milliseconds. So, I have a signal being a sum where k can be minus infinity to infinity or m. Of the plus m tau. Here m is integer. It's a number of pulses. If this generator would have a counter, m would be a number of switch. Time and at t capital is a period, in our case, 2 milliseconds. Can we now write this sequence as a Fourier row? Why not? It's a periodic sequence. Number of pulses. Let's try to perform a Fourier transformation on it. So, I will mark as omega divided by, it's a frequency, and complex amplitude of the harmonics number k, or complex amplitude at a frequency omega k will be I should integrate from 0 to period my signal multiplied by exponent of minus omega, and I should integrate in time. It's a classics of Fourier transform. And now, key moment. The problem is I don't need to deal with the sequence. I need one pulse. Take a look. I'll make a very simple change. I will increase a period. I will do it this way. See? It's a sequence. Now, what happened? No period found. See? For the scope, this is periodic signal. It has period, it has frequency, two frequencies. This one is not periodic. No period found, it's aperiodic. Periodic, non-periodic. What's the difference? For scope, time starts here and ends at this point. Nothing exists for the scope outside this line. It is end of scope memory. Everything outside of observation window, it's a window of observation. The time frame in which scope operates. Everything outside this frame is ignored. In fact, this pulse now it exists for the scope. Oops. I want to. At this moment, brains of the scope don't see no pulses inside the observation frame, so this signal is not periodic. Where is observation frame for our work, for us?
From 0 to period.
Where? No, we don't have any period.
From 0 to
In theory, see what's the problem?
infinity.
It's from minus infinity to plus infinity. For us, time. Okay, time is from the, if you believe, it's time from the creation moment until the doomsday. After the doomsday, who should care about some pulse? Yeah, it's Riders of Apocalypse. You open the window, oh my God, Riders of Apocalypse. What pulses? How is that? The same at the beginning. Before the world exists, no pulse. This means I can do it on my blackboard. I can do it in theory. I can increase period to infinity. This means what all repeating, all, let's say, replicas of the original pulse will be all before the creation of the world or after the doomsday. And my signal will contain only one original pulse. I will make the same trick what I did with the scope. No one knows what the second pulse will emerge. And no one will. Because when the second arrives, no one to observe it. So, I'll have something like this to divide integrate from minus infinity to infinity f omega kt and in time. Here, I have a tiny problem. 2 divided by infinity leads to 0. I will receive, appears what I'm receiving nothing. But wait a moment. I have all this part. I can use it to create an image of my signal in the frequency space. Such image called spectral function. It's a complex function of frequency and can be found as and that's infinity to infinity from my powers a power omega dt. Spectral function. It's a complex function of complex variable. It's complex, and it represents my signal in the frequency space. In our world, this function can't exist. It's a pure imaginable object. While for periodic signal we had a representation of real frequencies, this machine output is real. It exists in our world. Spectral function can't exist in our world. It's pure imaginable. So what's the idea?
Professor, UT and ST are the same thing?
No, S is a sequence. They all together is S.
One is
And one is U. This one is U, all together S. What's the idea? How can I use pure imaginable function? Remember, I spoke about transfer functions. We have some network. It may contain capacitors, coils, and resistance, and what else. If I can represent an input as a function of frequency, and my network can be represented as a transfer function, again of frequency, output will be input as a function of frequency multiplied by transfer function of frequency. So, if I have something like original time pulse, and I can use Fourier transform to create a spectral function, it's okay to use a spectral function as an input.
as an output.
And output will be spectral function too. If I'm able to, let's say, create an image of my pulse in a frequency space, it's a spectral function. Okay, let it be. I will multiply spectral function with a transfer, and I'll get output representation in a frequency space. I can perform analyze in frequency space not only for periodic signal, but for non-periodic. Okay, I'll get spectral function of the output. Where the dog is digging. How will I get it as a time function? In the imaginable world of the frequency function, everything perfect. But how I use it in mine, I'm here. I'm not a function of frequency, I'm a function of time. I live in time. I need a way to get results out of the frequency space to our time space. I need an inverse Fourier transform. For the spectral function, I just wrote a formula converting time function to frequency. Now I need an, let's say way back, how to get something from the frequency space to our time space. Okay. As it usual, way out is not so easy as way in. Pause. One moment. If we started from omega t being minus infinity to infinity, f power omega k. It's what we started with. From this we can easily understand what a value of harmonic, of classic Fourier rule at a frequency can be found as 2 divided by period spectral function value at a frequency if sequence is okay for us, no problem. Values of spectral function. So, if spectral function obtained as a Fourier transform, and it's okay for us to operate with sequence with the repeating time t capital, no problem, just take values of spectral function at frequencies of harmonics and you get harmonics values. Easy. At this point it's easy.
Professor, can you give an example of converting it into spectral function?
Yeah, I'll do it. Bit later. We will convert this one. And see impacts of period change. Everything planned. So, now we need this way out. We need inversion of Fourier transform. We need it. Let's try to write what we know about spectral function. So what was our way? We created a signal as a sequence of the pulses. Is it correct? Is it correct? We can explain or replace the sequence with the Fourier rule. It will be 1/2 sum from minus infinity to infinity. A power J k. It's a classic Fourier rule in a complex form. But values of harmonic factors or coefficients can be found as a values of spectral functions. So we will have 1/2 sum minus infinity, write infinity to infinity, 2 divided by time, spectral function values at a power of here it is. signal as a sequence of pulses, signal as a Fourier law, factors or coefficients of Fourier law as a values of spectral function. So what? Okay, you wrote a bunch of sums. So what? At first, let's try to see what will happen if we increase period to the infinity. Again, I'm shifting the next pulse beyond the observation line. So, shifting to infinity of some, let's say m, from minus infinity to infinity plus m will be original not e. It's good. We'll see only with M0. The next one, M1, will be somewhere. No one to see him. No one to bother about it. Now, let's try to understand what will happen if we move to infinity. 1 against sum minus infinity to infinity. Spectral function taken at values at power It's a bit confusing. What appears, what it moves to 0. But let's see. Let's try to look closer. And at close, we need to understand one moment. Remember our experiment with rectangular. We had a spectral line. Anyway, any periodic signal can be schematically shown as a line at 0, it's a DC component, 1 omega, 2 omegas, 3 omegas, and so on. The distance between line is nothing else to be divided by period. Is it? They go with the step 1 frequency. Single frequency, double frequency, triple frequency, and so on. So distance between spectral lines is 1 frequency. When we move frequency to infinity, these lines will come closer and closer. And at the end, what we will see? One solid figure. One uninterruptible solid figure. And our sum will become an determined integral in the frequency space. Our sum at the end, what will describe? this figure. When we imagine all these lines, the next, one to the next, one to the next, they all become a one, let's say, not a pattern, one, okay, it's H in computer-aided drawing. And they glued together to the one area. And the result of this sum will be field of this area. Let me free some space. So, I can write what when I push period to infinity, I'll need against P. Sum minus infinity to infinity values of spectral function at a frequency omega a power j omega t, and here I will have this will all glue together to 1 against what? Infinite spectral function of the frequency a power omega t d omega. Now I can write a finish form. 1 second, I will write it in more, let's say, more aesthetic way. So my pulse will be 1 infinity to infinity spectral function from frequency f power d omega. Here it is. It's our inverse Fourier transform. It's our way back. It is usable to make a note on one thing. There is one thing with spectral function. It's, let's say, inherited from the Fourier law in complex form. Moment is spectral function value at negative frequency is a conjugation at the plus omega. Sign changes sign at the imaginary part. If you don't like negative frequencies, just take double real part from 0 to infinity, frequency a power omega d omega. If you don't like negative frequency, take double real part and everything will be fine. Now, what about our yellow friend? What about our yellow friend? I have promised an example. What about our yellow friend? So we have big 0 when time is below 0 and e power of t when time is greater or equal to 0. Non-periodic signal. Here, in our case, of again once FC, but it's not important. It can be coil. Coil voltage will have the same exponential form. So, our yellow non-periodic friend. Can we please transfer you to the frequency space? What? You don't want? I don't care. So its representation in a frequency space will be starting at power omega. I need to start from 0 and end at infinity. Of a power omega t. Can I take it? We will integrate. Long heat. What will I get? T divided by alpha omega. I can draw it, but I can separate absolute value. I can write it as divided by square root alpha square plus omega square. A multiplied by a power not up tangents. Tangents it will be omega divided by alpha. The absolute value of it looks approximately like this. it will be spectral function divided by its maximum, and it's reached 1/2 at the point double of. Approximately like this. Look this. Absolute value.
Professor, how did you get to E over alpha plus j omega? The first step.
Yeah, the first step,
That's after integration.
group both exponents together, what will you get?
You have e to the power
A power,
minus alpha t minus j omega.
yes,
Then take t out, then you have
And?
alpha plus j omega.
yeah, and you will have 1 divided by,
Yes, e over.
and in from 0, where they are 1, to the infinity, when they will become 0.
Professor, isn't it minus infinity to infinity? It's
We
minus.
have to, we will see minus and minus,
Yes.
if I correct. So, what shall we do? Let's try to make it visible. To define some period of t. It should be -1 and minus at division. Let's say we have some period. This will give us an complex amplitude of the harmonic being 2 divided by period E divided alpha square plus t square multiplied by echo arctangents and once again divided by alpha. Here is my sequence. My scope is smart. Enough.
Professor, arctan what is that?
Huh?
Arctan what?
What? Sorry? Arctangents.
Arctangent.
It's an arctangent. Here I have a frequency.
So what's the value for tangent? Arctangent what?
Arctangents of this.
Okay.
And divisor is an alpha, and divided, in fact, it's a harmonics frequency.
Professor, but the other equation didn't have an arctangent in it. It's
Okay.
minus.
I'm just, this is G arctangents. I'm separating real and see, I have a complex function. I'm representing it in a polar coordinates, not Cartesian, to separate an absolute value. Why? My scope can perform a Fourier transformation, but it can display only values without angles. This red line is an A as a function of frequency. One second, please. See? The red cross, red mark.
So we will always have to use polar coordinates?
This mark.
So do we always have to use polar coordinates? Can't we just do it?
Bit different. I have absolute value of harmonic coefficient. As a function, it's in fact it's internal frequency of the scope. But for us, here is a conversion to the real kilohertz. See it at side. It's a position of the vertical line. So when I scroll, now it's 4 kilohertz. We will see later, I will show why in theory they should be ideal vertical lines. Why they are not so ideal? It's a problem of discrete processing. But it's a time. Our sequence, the yellow line is our sequence as a function of time. Red line is our sequence as a function of frequency, but in vertical line it's absolute value. Without angle. Scope can is unable to calculate angles. That's why I'm separating. In fact, we see only this time, this part. What we got? Sequence of pulse represented as a official, it's called function of discrete frequency, or discrete frequency function. In ideal world, it looks like now question, what will happen if we take t prime being 1/2 of the t? What will happen? Amplitude changes, but also frequency scale change. Take a look. See what happens? Time between pulse, 2 times short. I have, let's say, double the speed of pulse. And what happens with the spectral lines? The distance increases 2 times. 4 times. I can go in opposite direction. See what's going on? They move, let's say process goes in opposite direction. More pulse in the unit of time. The broader is spectrum. And in opposite, less pulses. See, it's going to be uninterruptible. For 1 pulse, spectrum, scope can only draw real frequencies, so for 1 pulse it will be something like this, uninterruptible line. More. Okay. They pulse glued together, but spectral lines are broad and broad. This analysis leads us to a very important thing. What in periodic process, broader periods means closer or narrow spectrum. So broader process needs wider, broader process needs wider spectra. Or on the other way, compressed process occupy narrow spectrum. They're going together.
Professor, even that looks like an exponential decay.
Yeah, at the end, there is actually it's not an complete exponent, but it's official. It's called curve of the second degree. Yes, it looks like exponent. What I want to say? I want to demonstrate effect of the change rate here. See, I can play with the change rate here. Either I will take another resistance box and I will show effect of the rapid change of alpha. I have a time. This box is 100 kilo ohms. I'll take another 100 kilo ohms. And I'll make something like this. Big capacitor. Resistance box of 50 kilo ohms. Resistance box of 150 kilo ohms. Somewhere. I'll have switch here. Okay. My pulse generator. Yes. And this will be our signal. But I'll need a switch. Let's see what I can do.
Professor, in the example, we didn't convert it back to from the spectral function.
We didn't because we knew the result.
Okay.
Later, see, this Fourier transform, we can make a next step and it will become Laplacian transform. And I'll show how to perform numerical inversion of Laplacian transform. There is one problem with Fourier transform. If we use something like this, switch on, it is not compatible with Dirichlet conditions. It's out of Dirichlet conditions. So classical Fourier transform will not work in case when we switch off. See, in this case, it's decaying exponent, and we have a right border 0. It leads to 0. So Dirichlet, let's say, convenants are fulfilled. If we try to switch on process like this, let's say capacitor not discharged but charged, we will go outside of Dirichlet conditions or convenants because we will have, in theory, infinite energy. Laplacian transform introduces a way to artificially create the right margin. So, when we need, let's say, a super tube for transients, simple Fourier transform may not work. So we will see how to deal with any process using Laplacian transform.
So after we use the Fourier conversion, we use Laplace.
Let's say Fourier integral, this form of Fourier is one of the let's say forms or one of the ways of Laplacian. Laplacian transform is a no, let's say higher level.
Okay, so it's a substitute for using the spectral method.
Periodic signal is a, let's say, base level, Fourier higher level, and the highest is Laplacian. Plus.
Is it easier than doing it this way?
It depends. For ordinary, let's say voltage current ordinary network, it's enough with traditional this transform. Spectral functions and so on start to play when we deal with when we try to deal with transients. Switch on, switch off, operation of power converters. What will happen when we switch on? Transients. Let's say it's less popular, and often people even don't try to perform an analytical analysis and switch to numerical analyze. Let's say something like LT spice, try to solve it numerical. But without understanding the picture, it's very easy to get an absolutely disastrous results, because numerical solution of differential equation often produces so wrong results. Okay. Let's go step by step. I want to show depends with a process ratio and its let's say occupied frequency range. It is very useful sometimes to look not from the time perspective, but from the frequency. The simplest thing, tones. When I can say some system amplifies low frequencies, what does this mean? It will amplify, but suppress. When we speak tones, we also speak in frequency terms, not in time. Well, we live in time, but tone is a frequency. Okay, what I'm trying to do? I want to assemble a network where I can switch come on. I want my network. Where are you? Oh. Okay. This one grounded. This one will be grounded, and the second one, and the second one goes. I have promised 50 kiloohms. 50. So the second one goes there. Okay, what I have now? 250. I need to switch with the scale in a frequency.
So it's 150 and 50.
Yes, this one is 50 and I have sum of 150. Altogether 200. Now, I have 200 and I switch to 50. See? Process goes sharpens. And what we see in frequency? See? It's narrow, it's widens. Sharper change means wide frequency range. You had some system, everything was fine, and you install beta switch. Beta, not worse. Which switches faster. It switches faster means wider frequency range, and disturbance causes your system to fail. Or resonant history of power system designs knew a lot of cases where resonant circuit was at some 100, 200 kilohertz. At a low frequency, everything works fine. When at computation appears components, they cause resonance and fast degrade of semiconductors. It's a problem with large wafers of high power semiconductors are quite sensitive to high frequency components. Because high frequency component is not distributed evenly. At a low frequency, current distributes evenly on all the surface. At a high frequency, this distribution is not evenly. It's a kind of waves, and you can find a so-called hotspot where this semiconductor structure is overloaded. It overheats, degrades, and
But Professor, if the resonance frequency is surpassed, then also it will be okay?
it's okay. You need, when you see something like this, you have a range of frequencies. If we have network, for example, something like that, it depends on inductance capacitance. It will be some frequency or multiple frequencies. If we have coupled networks, it may be 2 or 4 frequencies. And if one of these exactly at the resonance, we are in problem. What we will need to do? Snubbers. This idea, artificial networks to dampen. Usually they can capacitor resistance. Some also use diodes. Snubber networks to suppress contour quality, to suppress high frequency components. You see, slow process, quite short frequency. Let's say tail. You see, it's quite fast decay. I change L for time. Now process goes much faster, and you see elongation of this frequency tail. So process short, process in time, it takes less time, it's short. And in frequency space, it takes wide or broad frequency range. Same thing with capacitance. I have changed 10 times. See how frequency range broadens.
What was the capacitance profile that you changed?
1 nanofarad. This one.
1 nanofarad.
It's adjustable at the full scale. It's 1 nanofarad. And some 50 picofarads now. Approximately. Wires also should be counted at a low capacitance. It's approximate. Okay.
So we can either decrease the capacitance or close the switch. Same effect.
Yeah, we can have same effect. And you see how broad is. I have increased capacity. I have increased resistance. No, I will not touch it. No, it's switched off. It's 220. Possible. Вот Давыдов Добровольский ordered the switch in 1926. Dobrovolsky helped to buy in Germany set of equipment for university. I think this switch is from that time. Good switch. Okay. Where am I? Oh! I think it's enough for today. I can end my stream. Maybe someone I have 0 viewers, but who knows? I need to take one moment. Zero concurrent views. I'll put it in this e-learning system for any case. Maybe it will be usable.